Hello everyone. This is the second episode in our series on the moons of our solar system. In the last video, we introduced the most volcanically active body in the solar system, Jupiter's moon Io. In this video, we'll talk about a moon with a completely opposite character to Io, its sibling moon, Europa. Humanity first discovered Europa over 400 years ago. On January 7, 1610, Galileo, at the University of Padua in Italy, used a telescope with 20x magnification to observe both Io and Europa. However, the two celestial bodies were slightly overlapping that night, so he couldn't see them clearly. It wasn't until the next night, January 8th, that he officially confirmed Io and Europa as two separate celestial bodies. Besides Galileo, German astronomer Simon Marius also discovered Europa in the same year. It was he who proposed naming it Europa. The name Europa comes from Greek mythology, one of Zeus's lovers. In fact, the names of all four of Jupiter's largest moons come from Zeus's lovers. As we've mentioned before, Jupiter in Roman mythology corresponds to Zeus in Greek mythology. However, in Greek mythology, these four characters were either abducted or tricked by Zeus. Ganymede was even male. In short, none of them had happy endings. So, Marius naming them this way might have been a hint that getting close to Jupiter is dangerous. Europa is the smallest of the four Galilean moons, even slightly smaller than our moon, with a diameter of about 3,120 kilometers. It is the sixth largest moon in the solar system. Don't let its size fool you. It has considerable mass. If you add up all the moons in the solar system smaller than it, their combined mass doesn't equal Europa's. Based on its density, its composition is very similar to terrestrial planets like Earth, consisting mainly of rock with a metallic iron core. It is estimated that Europa's surface is a layer of water about 100 kilometers thick. The upper part is completely frozen, forming the ice shell we see, while the lower part is a liquid saltwater ocean hidden beneath the ice shell. So, what evidence do we have for an ocean beneath its ice shell? It's because the Galileo spacecraft discovered that Europa has a magnetic field. Some might say, what's so strange about having a magnetic field? Many celestial bodies have them. Note that Europa's magnetic field is different from Earth's. Earth's magnetic field is a primary field generated by the motion of its core. It's stable, has north and south poles, and very clear magnetic field lines. However, Europa's magnetic field is not self-generated. It is an induced magnetic field, created by induction from Jupiter's magnetic field. This induced field is very unstable and changes with Jupiter's magnetic field. So what causes this induced magnetic field? A very strong possibility is the existence of an electrically conductive liquid layer inside it, a saltwater ocean. There are a few other bodies in the solar system with induced magnetic fields, like Titan, which we've discussed, and Ganymede and Callisto, which we'll discuss later. These three also have induced magnetic fields, so they might also have internal saltwater oceans. But by comparison, Europa's induced magnetic field is the clearest and strongest. Furthermore, Europa's ice shell has experienced flips of nearly 80 degrees. This indicates that its ice shell and interior are decoupled and slide past each other. The shell is floating, not stuck to the mantle like Earth's crust. That's why scientists widely believe that there must be a liquid water layer beneath Europa's surface. But here's the problem. Europa's surface temperature is around -163 degrees Celsius at the equator and even lower at the poles, only -223 degrees Celsius. Its surface is permanently frozen. So what allows the water under the ice to remain liquid? There are two main reasons. The first is, again, tidal heating. In our last video, we explained that Io's intense volcanic activity is due to tidal heating. Jupiter's gravity, combined with the orbital resonance of Io, Europa, and Ganymede, causes Europa to be constantly stretched and compressed as it orbits Jupiter. Both its ice shell and its rocky mantle generate heat from this stretching and friction. Besides the friction heat from tidal forces, in 2008, scientists discovered a hidden heating mechanism on Europa, planetary tidal waves within its internal ocean. Although Europa looks rigid, its axis of rotation is not perfectly vertical, but slightly tilted by just 0.1 degrees. Because of this tiny tilt, slow but massive ocean waves are formed in its liquid ocean. The technical term for these is Rossby waves, also known as planetary waves. This phenomenon was first discovered in Earth's atmosphere in 1939 by American meteorologist Carl Gustav Rossby. Many of you may be hearing about this for the first time, but it's related to our daily weather, wind, and the movement of cold air masses. It's a type of inertial wave that appears on rotating celestial bodies. They exist in Earth's atmosphere and oceans. In theory, any rotating body with a certain axial tilt and flowing air or liquid will have Rossby waves. These waves move only a few kilometers per day, so they are very slow, but they store an astonishing amount of energy. According to simulation results, the heat generated by these ocean currents on Europa could be 100 to 1,000 times greater than that from tidal heating. So, this energy may be the main heat source that maintains Europa's liquid ocean. What's even more exciting is that this heating might not be confined to the liquid ocean itself. If enough heat is transferred to the rocky seafloor, it could trigger phenomena similar to Earth's hydrothermal vents, geothermal activity like deep-sea volcanoes. In Earth's deep seas, scientists have found many peculiar life forms near these hydrothermal vents. They survive without any sunlight, relying solely on geothermal heat and chemical reactions. Therefore, if such hydrothermal vent environments also exist on Europa's seafloor, it would be a very promising place for life to emerge. This is precisely why it has become one of the top candidates in humanity's search for extraterrestrial life. Europa is the smoothest celestial body in the solar system, with very few mountains or impact craters. Its albedo is 0.64, meaning it reflects about 60% of the sunlight that hits it. In comparison, the moon's albedo is only 0.07, reflecting just 7% of sunlight. This indicates that its ice surface is generally very clean. If the ice had many impurities, its albedo would be much lower. Moreover, the scarcity of impact craters on its surface suggests that Europa's ice shell is not only clean, but also fresh and active. Whenever a meteorite strikes, its ice slowly flows to fill in the crater. According to simulations, the age of Europa's surface ice shell may be only 20 to 180 million years old. On a cosmic scale, this is extremely young. If you compress the universe's entire 138 billion-year history into a 100-year human lifespan, the ice on Europa's surface would be less than a year old, and in some places, just born 2 weeks ago. We first saw Europa up close in December 1973, when Pioneer 10 flew past Jupiter and took a picture of the moon. But the distance was great, and the image was very blurry, making it impossible to see the surface details. The first time we truly saw its surface clearly was in 1979, when Voyager 1 and 2 sent back a large number of high-resolution images. In these images, we can see many sprawling stripes on Europa's surface, which are its most prominent feature. These stripes are generally 1 to 2 kilometers wide, with the widest reaching up to 20 kilometers. Initially, scientists thought these stripes were just visual differences caused by varying ice compositions and their ability to reflect sunlight, technically known as albedo features. However, later analysis of radar data revealed that these stripes are actually cracks in the crust. The ice on either side of the cracks has clearly moved, as if torn apart. And in the middle of these stripes, you can see a brighter band. This is likely formed by salty water from the subsurface ocean erupting through the cracks and refreezing. This process is very similar to the formation of mid-ocean ridges on Earth. Earth's oceanic plates are pushed apart by magma, and new magma emerges and cools to form a new ocean floor. The difference is that on Europa, what erupts from the cracks is not magma, but salty water from below. Scientists originally thought these cracks were caused by Jupiter's powerful tidal forces. But because Europa is tidally locked, it always keeps the same face towards Jupiter, just like the Moon does with Earth. Logically, this tidal locking should produce a predictable pattern of cracks on Europa's surface. That is, the direction of these cracks should follow a regular pattern. But strangely, scientists found that only the most recent cracks fit this theoretical prediction. The older the cracks, the more random their orientation and the greater the deviation. A plausible explanation is that Europa's outer shell rotates slightly faster than its interior. Calculations suggest that about every 10,000 years, Europa's outer shell completes one extra rotation compared to its interior. As we just said, Europa's ice shell floats on the internal ocean. So, as it rotates, the outer shell is also slowly sliding. Although the satellite's overall orientation relative to Jupiter remains locked, if the outer shell rotates a little more than the interior each time, the direction of the cracks left by Jupiter's tidal forces will also be different each time. Besides the cracks, another prominent feature on Europa's surface is the many dark spots of various sizes. Some of these are bulges, while others are depressions, typically about 10 kilometers in diameter. Scientists speculate that these dark spots may be formed by warmer ice from beneath the shell slowly pushing upwards and breaking through the surface ice. This is similar to how volcanic domes are formed on Earth when magma pushes upwards. But if this warm ice upwelling is very strong, it won't just create a bulge. It might shatter an entire section of the ice sheet, creating a new type of terrain called chaotic terrain. Look at this image. The messy-looking area in the middle is a classic example of chaotic terrain on Europa, called Connemara chaos. Doesn't it look like a pane of glass that was shattered and then haphazardly pieced back together? In fact, this surface may have once been a flat ice sheet. But due to intense internal activity on Europa, the ice sheet suddenly fractured. After fracturing, it refroze and became jammed together, resulting in this chaotic region. Therefore, Connemara chaos is often cited as evidence for the existence of a liquid ocean beneath Europa's ice sheet. If you look closely at photos of Europa, you'll notice it has almost no large craters. But there is one striking exception, the Pool crater. It is one of the best preserved craters on Europa. It looks a lot like the Tycho crater on our moon. It's estimated that the Pool crater is about 18 million years old. It has a diameter of about 26 kilometers, with a few small central peaks about 600 meters high. Interestingly, these central peaks are taller than the crater's rim, which is quite rare for craters in the solar system. In addition, scientists speculate that Europa's equator may be covered with ice spikes up to 15 meters high. These spikes, called penitents, are not built up, but are sculpted over time as the ice surface sublimates under continuous sunlight, creating rows of sharp, blade-like vertical structures. Although we have not yet captured images of these ice spikes, both radar and thermal imaging results are highly consistent with such a structure. Having discussed Europa's subsurface ocean and surface, let's now talk about its atmosphere. Europa's atmosphere was discovered in 1995 by astronomers using the Hubble Space Telescope. Its atmosphere is mainly composed of oxygen with a small amount of water vapor. However, this oxygen is not produced by biological activity. Instead, it's because Europa is constantly exposed to solar ultraviolet radiation and Jupiter's magnetic field. The UV rays and charged particles from Jupiter's magnetosphere constantly bombard Europa's ice surface, splitting the ice into oxygen and hydrogen. This process is called radiolysis. You might wonder, where did the hydrogen produced from the split go? Well, because the resulting hydrogen is so light, it quickly escapes into space. The relatively heavier oxygen lingers temporarily at an altitude of about 190 kilometers, forming the atmosphere we observe. However, these oxygen molecules don't stay there forever either. They either drift away or fall back to the surface. So, Europa's atmosphere is extremely thin, even thinner than Io's. If Io's atmosphere is a mist spewed from volcanoes, then Europa's atmosphere can hardly be called a mist. It's more like vapor from surface decomposition that floats for a while before dissipating. Plus, its gravity is too low, only 13% of Earth's, so it can't hold on to a thick atmosphere. Therefore, there is no wind, no rain or snow on Europa, and even the sky is black because its atmosphere is too thin to scatter light into a blue color. For the past 50 years, humanity has been searching for extraterrestrial life throughout the solar system. We have sent robots to land on Mars to probe its rocks, and we have sent probes to fly by Venus in search of traces of water. We've even brought back samples from distant asteroids to Earth. These are already remarkable achievements. But so far, we have not found any true extraterrestrial life. And now, we have a new hope, the Europa Clipper. This probe weighs 6 tons, making it the largest probe in NASA's history. The entire mission costs $5.2 billion, also making it one of NASA's most expensive projects, not including manned spaceflight. Originally, NASA planned to launch the Europa Clipper on its own SLS heavy-lift rocket, which is hailed as the most powerful rocket system on Earth. But in 2021, they suddenly decided to switch to SpaceX's Falcon Heavy rocket. There were 3 reasons for this. First, the price was too good. An SLS launch costs billions of dollars, while a Falcon Heavy launch costs only $178 million. Just on the launch alone, they saved $2 billion. Second, the SLS might not have been available. This launch system is prioritized for the Artemis moon landing program, and NASA itself wasn't sure if it could spare a slot for the Europa Clipper. Third, and most critically, was the safety issue. The SLS uses solid rocket boosters, which provide immense thrust, but produce intense vibrations upon ignition. The scientific instruments on the Europa Clipper are extremely delicate. If they were shaken so violently, they might be rendered useless before even leaving Earth's orbit. However, although NASA saved $2 billion on launch costs, it wasn't without a price. If they had used the SLS, the Europa Clipper could have flown directly to Jupiter, arriving within 3 years. After switching to the Falcon Heavy, due to insufficient thrust, it has to take a longer route. It will first pass by Venus and Earth, and even Mars, using the gravity of these planets to accelerate it on its way to Jupiter. This extends the entire flight to 6 years. But for NASA, this trade-off was worth it. After all, the money saved could be used to build several more probes. On October 14, 2024, the Europa Clipper was officially launched from the Kennedy Space Center. It is expected to arrive at Jupiter in April 2030. Powering a probe on a mission so far away is a major issue. The sunlight reaching Jupiter is only 4% of that at Earth, meaning solar power becomes very weak. NASA initially considered using nuclear power, specifically a radioisotope thermoelectric generator, RTG, fueled by plutonium-238. We've talked about this before. The Voyager probes use RTGs. But for the United States, RTGs are both expensive and scarce. NASA currently has only 5, one of which is reserved for a Mars rover. Later, scientists realized that although solar energy at Jupiter is weaker, it is still sufficient to power the Europa Clipper and, crucially, at a lower cost. So, NASA ultimately decided to power the Europa Clipper with solar energy, just like the Juno probe. They equipped it with 30-meter-long solar panels. Although these solar panels are much heavier than a nuclear power source, after design optimization, the total weight of the spacecraft is still acceptable. The Europa Clipper is also equipped with 9 scientific instruments. These 9 instruments form a comprehensive detection system, covering everything from Europa's atmosphere to its surface ice shell and its internal ocean. The goal is very clear: to search for the possibility of life and to prepare for a future landing. The Europa Clipper will also search for plumes at the cracks in Europa's ice shell. Europa's plumes are different from Io's. Io spews fire, Europa spews water. Sometimes Europa directly ejects water vapor and ice from its surface into space. The first to discover these plumes on Europa was the Hubble Space Telescope. In 2012, Hubble observed a massive water plume near Europa's south pole, reaching a height of 200 kilometers, more than 20 times the height of Mount Everest. The formation of Europa's plumes is also related to Jupiter's tidal forces. It's estimated that the tidal forces experienced by Europa are about 1,000 times stronger than the Moon's gravitational pull on Earth. Under such powerful tidal forces, Europa's plumes can eject 7,000 kilograms of water vapor per second. Similar plumes exist on Saturn's moon Enceladus, which erupts at a rate of about 200 kilograms per second. This means Europa's eruption rate could be 35 times greater than Enceladus's, or even more. But this is just an estimate and has not yet been confirmed by a probe. If this can be confirmed by the Europa Clipper, then we might not need to land on Europa, nor would we have to drill through its tens of kilometers of ice. We could just have the probe fly through a plume. To put it dramatically, we could just reach out and collect a sample of its subsurface ocean directly. Then, we might finally know if there is extraterrestrial life on Europa. It's like how scientists on Earth use drones carrying petri dishes to fly through the waterspouts of whales to collect all sorts of biological information about them. Let's be honest, we missed the launch of many past probes. We're mostly looking back with hindsight. But this is a probe I'm truly excited about. It's the first probe of our era with the core mission of searching for extraterrestrial life. I really hope it brings back something astounding. Starting in April 2030, it will officially enter orbit around Jupiter. Over the next 4 years, it will conduct 50 close flybys of Europa, with the closest approach being only about 25 kilometers from the surface. Then, according to the plan, after its mission ends on September 3rd, 2034, scientists may have it crash into Ganymede. This arrangement is actually a form of planetary protection. Scientists are concerned that residual Earth microbes on the probe could contaminate Europa's subsurface ocean. Although this possibility is very, very small, even the slightest chance must be avoided. So they came up with this kill two birds with one stone plan. If the Europa Clipper's mission is not extended, they will have it crash into Ganymede. This way, the European Space Agency's JUICE probe, which will be there, can take the opportunity to analyze the resulting ejecta to study the chemical composition of Ganymede's surface. This is because Ganymede is also presumed to have a subsurface ocean, but its ice layer is much thicker than Europa's, so in theory, it can protect its internal water from impact contamination. Alright, that's all for this video. In the next video, we'll talk in detail about Ganymede, the largest moon in the solar system. Thanks for watching, and see you in the next video.